In this video we're going to be looking at op-amps from an ideal perspective. So we're going to be looking at the approximations that we can make in order to simplify our analysis of an operational amplifier circuit. So in essence, our op-amp is a three-terminal device. We have the positive or non-inverting input, the negative or inverting input, we have our output, and we normally have a couple of voltage rails as well. But for the ideal sense, we're actually going to ignore those two voltage rails and just focus on the three-terminal device. Alright, so that's approximately equal to, and this is a common approximation for it, where we have the three terminals. I might just draw that one out here. Plus and minus. Okay, so there's a voltage source. Alright, so there's our output, our VP, our VN, as measured between that point and ground, and that point and ground as well. And what I want you to see from this diagram, so this is an ideal approximation, a few things. First of all, these two inputs, the positive and negative, or non-inverting and inverting inputs, they're not connected to anything. Alright, you can actually see there is no physical connection here. So, the first approximation, so approximations of an ideal op-amp. First one that we can state is that the current flow IP equals IN equals 0 amps. Alright, so we're saying that the current here, IP and IN, is 0. Alright, they're not connected to anything, very high impedance here with respect to ground, and therefore 0 current flows into the terminals, these guys here, of our op-amp. Right, so that's the first approximation we can make. From that, we can then say that the input resistance looking into the op-amp, right, so if I was to take a multimeter between here and ground, okay, so I had an ohm meter attached between those two terminals, I would see very, very large impedance, okay, approximately equal to infinity. So the second approximation we can make is that input impedance, and actually I'm going to call that Zin, or it could be Rin if you prefer, is equal to infinity. And that obviously relates to that first approximation we've made there. If the input impedance is infinite, therefore no current can flow, and therefore equal to 0 amps. Second one is, you'll notice in this model, third approximation, you'll notice in this model that there is no internal source resistance. Alright, so there's no Thevenin resistance equivalent in the circuit. So that means that the current flowing here is not limited by any source impedance. Okay, this being our voltage source here. So therefore, Z out is equal to 0 ohms. Right, so the output resistance, looking from this point here to the output, something we can't easily measure without an external circuit, is equal to 0 ohms. And remember, that's good for connecting to circuits which have some sort of capacitance on the output, because that means that our time constants are much shorter. Alright. Further approximations we can make, we can say that the output voltage is independent, so it is not proportional to the output current. So in an ideal world, we can supply as much current out of this device because Z out is equal to 0, and it will not affect the output voltage. Alright, So the load regulation, if you think of this as a power supply, is very, very good. Right? So V out is not proportional to I out. There is no relationship there. They are completely independent. 5. This device here should operate independent of applied frequency. So if we were to apply a sine wave to Vp and let's say 0 volts or ground to Vn, no matter how high the frequency applied to Vp, okay, output gain will be the same. So what we're effectively saying is the bandwidth of this device is infinite. Alright, so bandwidth is infinite. If we were to draw a frequency response curve, so increasing frequency versus gain, that could be in decibels or it could be just a ratio, we would expect a flat line all the way up to f equals infinity. Okay, so no matter how high f gets, output gain or the voltage gain in this device will be the same. It will be a constant through here. 6. The actual gain of this device, usually given by letter A, and I'm going to use the subscript V because this is a voltage gain, is also very large. And in an ideal op-amp, we could say that it's actually infinite. So the output voltage is the infinite, or infinity times the difference between the input voltages. So it's not practically like that, but in an ideal sense we can say that the voltage gain is very, very large. And remembering that V out is equal to AV times Vp minus Vn, as we saw in the differential amplifier overview. Alright, so if AV here is very, very large, then whatever the difference is here will be multiplied by a very, very large number in an open loop configuration. Alright, we're not talking about feedback circuits, we're just talking about the circuit as it is here. Okay, the op-amp in isolation. 7. Common mode gain is 0. Now what we mean by that is that when Vp equals Vn, then according to this formula up here, V out should equal 0. Right? Because effectively it's the gain multiplied by the difference in voltage. So a perfect op-amp, or an ideal op-amp, where the voltages are exactly equal to each other, will give us 0 times the gain, doesn't matter what the gain is, gives us an output of 0. So the common mode gain, when both inputs are the same voltage, is equal to 0. And the final approximation that we're going to make is what's known as the virtual short. Now, I'm actually going to draw a new diagram for this. Now, what we've seen so far is that we can model the op-amp as a 3-terminal device, Vp, Vn, and V out. Now nothing there changes, alright? We can still say that okay, the current here is equal to 0 and the gain is equal to infinity and so forth. So all those same approximations hold. But if we re-examine this formula, V out is equal to the gain times the difference between the input voltages, then this is where you get one further approximation which allows us to have a virtual short between Vp and Vn. Alright, so what we're basically saying is the virtual short, and we use the term virtual because it doesn't actually exist, but it helps us in our analysis to think of this as being here. If we have a look at this configuration with this formula, if we say that Vout is finite, okay, it's a finite voltage, then for a large gain, these two must be very close to each other, close in value, and thus shorted together. Alright, so one approximation we can make is that the voltage Vp must always equal the voltage Vn. Alright, that helps in our analysis of working out the gain of a particular operational amplifier circuit. It's virtual because it is not there in reality. Okay, and make sure that equals 0. It is not there in reality, but it is an approximation that we can use. So to summarize again, our op-amp with its non-inverting and inverting inputs has one output. It can be modeled as a 3-terminal device where the output voltage is related by this equation here. So the gain times the difference between the two inputs, just like we saw in the differential amplifier review. And the approximations we can make are based on primarily looking at this circuit. Okay, these two terminals are not connected to anything, therefore there is no current flow. And therefore there is very high impedance between that point and ground, as I showed you in this diagram here. There is no resistance in series with the internal voltage source here, so voltage controlled voltage source from your circuit theory, and therefore the output resistance is 0. The amount of current flowing out of the op-amp is independent to the voltage. Alright, so there is no relationship, there is no constraint that says, well, if the current goes up, the voltage falls away approximately. Okay, there is independence between those two variables. We had a look at the frequency response, and we saw that the gain stayed the same regardless of frequency, all the way up to infinity, from 0 through to infinity. So not only can we amplify DC, but we can amplify signals up to infinite hertz in the ideal sense. We saw that the gain of this device is very large. In an ideal sense, it is approximately infinite, or there's no approximate than that, it is infinite. And we also saw that the common mode gain, when both inputs are the same, according to this equation here, this term will go to 0, so no matter what the gain is, our outputs should be 0. So the output under a common mode situation, the same input applied to both, should be equal to 0, and therefore the gain in that circuit is 0. And I also showed you how we can approximate the circuit using a virtual short. When we assume that the output voltage is finite, we have a very large gain, and therefore these two values must be very close in value, and therefore shorted together in a virtual sense.